So, hello everyone, welcome to my talk. First of all, who am I? I'm Sven. I have been a game developer for most of my life. I've started out in the Half-Life 2 modding community in my school times. First introduced to Unity in the university, and later on, about 10 years ago, I joined Camera Entertainment, where I at first became not a graphics programmer, but a technical artist. But about 2 years ago, I noticed that I was writing more shaders in Rider than I was in Amplify, so I decided to change my title to graphics programmer. What are we today talking about, or I'm talking about? I'm talking about Songs of Silence. For a strategy game, we have a turn-based strategy part, a real-time auto battle combat. We are in a high fantasy setting. We have some Lovecraftian horror elements in there, though, and it's all packed in this beautiful art-nouveau style, influenced by people like Alfons Mucha and Gustav Klimt. On a technical side, we are on Unity 2022.3. We use the universal render pipeline, though most of the shading has been replaced by some different shading techniques. We have released for PC, PlayStation 5, and Xbox. We are currently actually free on the Epic Games Store until tomorrow. But just to get an impression what the game is like, I'm just showing a short trailer. So, as you can see, there are quite a lot of effects in there. And we're talking about 4 today specifically, the fog of war, the silence, the title-giving silence, a little bit about grass, and because grass is not interesting enough on its own, we are going to talk about trample on it, and we're talking about light veins. Those are 4 effects that share some principles, that have all of the uniqueness, and I'm pointing out when there are some shared and unique stuff. This presentation is a little bit all over the place about what level of detail I'm going into, so I hope everyone can take at least something out of it. So let's just start with the fog of war. Now the game designer comes to me, we need a fog of war. What do we have? We have a fog of war which has 3 states. We have a covered state, we have an uncovered state. There is a classic state that we actually don't have, which is the explored state. Whenever you have explored something, it's basically forever visible. But even if it's officially not a state, but something that we have to convey in this is the out of playable area, the map borders. So how do we do this? We basically have a big bit array that is on the CPU side, which is just saving whether a certain pixel is, it's a 128 by 128 binary, let's call it texture, which says, is it uncovered or is it not uncovered? And the map border is just a rectangle, so start position size. And with this, we start the rendering. I'll go basically through the 3 steps that are happening. The first one is what initially happens when you transfer from the CPU to the GPU. First of all, we're just copying the data. The bit array gets put into a compute buffer. Compute buffer gets to the GPU. And we then start to process it. It's pretty low res. We sample it and we calculate a distance, signed distance field. So basically, the distance to the border. Of course, copying the data because it's just 1 bit per pixel is pretty lightweight, goes fast. The calculation of the signed distance field is, on the other hand, very slow. Because we have a very big radius on this and we are not using a brute force approach, there is also not a classic there are some classic optimized algorithms, but we're in a very big area. And instead, I'm using a stochastic algorithm here, which is basically just sampling, and whenever the state changes, the radius in which we are sampling gets smaller. This has pretty good results at the edge. It has not so good results the farther away you are from the border. There are some artifacts, but they are basically quite hidden inside of other noise effects. For the actual playable area, we are saving this, we are rendering this out into the very same texture in the blue channel. And in the green channel, we have the SDF. In the blue channel, we have the map border. And this is basically just the rectangle, a little bit smoothed out, added a little bit of noise so it looks a little bit more natural and a little bit less straight, so it's just a little bit more natural. So the next thing is we are now playing the game and we move an army. And of course, if you've seen it uncovers. We actually have a nice thing that we don't have a permanent update. We can limit this to when an army is moving. And we are actually not updating it when the army is moving permanently, but just in the moment that the army is basically sent on its way. We do the process that we just did again, and basically we take the previous and the next state and just do a linear interpolation over time. Simple, works out pretty nice, surprisingly. We do then a remapping of the signed distance field. We don't do it every frame. We could do it every frame, but we don't do it here as a preparation measure. We basically convert the signed distance field into the actual height of the fog of war, and we also save basically masks for 2 different noise textures, one for close to the border and one for the far away area. And when you now take this, we basically have the texture on the left. The map border is now in the alpha channel. We now create a third, and the next texture. We basically you are using ray matching for the fog of war, which of course is very expensive. So we want to do as little as possible in the ray matching. And this is why we pre-calculate all of the noises, all of the stuff that is needed there down, so we can reduce it at 1 sample per sample inside of the ray matching. And yeah, you see the noise textures. One is high density, high contrast. One is very low contrast and is for the far away area. So just it's a little bit interesting to look at. This texture is limited to the visible area. I'll talk later about this, but keep in mind the term frustum space. I'll get back to it later on. So we now go to the actual ray matching. This happens, of course, as the previous step, every single frame. This is a step that takes place between the opaque and the transparent pass. It uses the camera depth, and it renders at half resolution. Most ray matching today is done at half resolution. It just is a nice sweet spot for quality and actual rendering rendering performance. Demand. In this rendering pass, we render out, of course, the color values. We also render out, as you can see, an alpha channel. It's not actually rendered full screen. It's actually plane that is rendered here. And the same plane we use then in the transparent pass to compose it together. It's just an alpha blending. There is an additional step that is not actually part of the Fog of War. We have a plugin called Butofog, which our artists really like, which is just also some kind of distance fog, a little bit noise. And we put it on top of the Fog of War just to give this extra edge of having the shapes of the terrain visible through the Fog of War, so you kind of don't see what's underneath there, but you get an impression. So we actually have two sides of the map. We have a universe which has two worlds, one in the light, one in the dark. The light side, of course, uses all of the fog like you've seen. The dark side uses the same techniques, but the lighting calculation is quite different because in contrast to the light side, which is, of course, lit from the top, the dark side is lit from the bottom. You need to transition between these worlds, and we actually do it in a way where both map sides are displayed side by side. That you can just zoom out and you see basically both of your map side, the dark side and the light side, just besides each other. Now, of course, comes the problem. We need a transition, a smooth transition. You cannot, of course, blend ray matching shader. That would be quite devastating for performance. So instead, simple trick, screenshot of the light side, screenshot of the dark side. There is no area where you can actually cross directly on the map. There is another mechanic for this. Just Photoshop, have a gradient, and fade them out to the borders. We lay it on top. It works out nicely, as you can see on the right side. Pretty simple trick. So we're going to the silence. The name-giving silence. What is the silence? Let's just show. You can see the location is now in the silence. It's the floor has changed. The silence is actually in our world a corrupting force that's permanently, basically eating away in the basically eating away the magic energy of the world, and it's almost alive. It should feel alive. And it also needs to change through gameplay. We basically have two types of this. We have the silence that for story missions, a game designer can just pre-paint. And we have dynamic ones, which are created by a mechanic called purgatories. Now, there is a small gameplay thing where a location is either in the silence or out of the silence. I'm basically changing the data that I'm getting to a way where if the location is in the silence, it's completely in the silence. If the center is not in the silence, it's not in the silence at all. I'm just changing the whole area. Main thing is here is, as previously, we again have a texture. This time also with a signed distance field from the border. With a pre-painted silence, we just calculated at the start of the game. With the dynamic ones, we only have circles and lines, so we don't actually need to actually calculate the signed distance field. We actually just render circles with a smooth radius, and this also gets the job done here. So we have a light fake signed distance field. So we are now at the first iteration. We have this texture. We want to render it. This is actually the oldest screenshot in this whole presentation. We started out, of course, with recoloring the existing textures, removing the grass, but mainly recoloring everything. And there were some problems with this approach. First of all, the border of the silent distance field was pretty, well, not that very hard. It was very performance intensive. We basically, again, wanted to get this calculation out. We also have a problem where we have the light and the dark side, which are texture-wise on a totally different value level. And this means that the same color remapping that we used on the light side didn't work for the dark side and vice versa. So we got to a solution. The solution, first of all, for the textures, we gave it over to the artist. Now every map of ours has two textures, two diffuse textures. One is for the regular visuals, one is for the silence version. So this way we don't have any problems with the light and the dark side and values, and it just looks like the artist wanted it to look. Second thing is we get the SDF, and as with previously, we basically recalculate a texture mask once that we just have to apply, and well, it then basically gets applied. Well, why is this actually cheaper? Basically, we are pre-generating this mask and can use it everywhere instead of inside of the terrain shader. And that is by what I teased as frustum sprays. Of course, it's the term is kind of wrong, but I still use it. It's basically I take the view frustum of the camera and get it on the map and calculate an area that we need, a rectangle that we actually can see. I give it a little bit of buffer because if I'm basically checking the collision with the ground layer, if the ground is a little bit lower or in the back or higher in the front, there can be some area out of it visible. So I gave it a little bit of buffer. But this rectangle, every detail calculation is basically not performed in the final frame, in the terrain shader, or in any other shader, but we are creating an in-between mask in this, and we have this room that I have a shader library that you can access at every point. We are not even transforming with matrices anymore. It's just an offset and a scaling, so simple multiply add. Second thing, Cameraless rendering. Sounds scary, but I guess everyone who's ever done a blit operation has already done this. It is pretty easy. You just render. You can just have a command buffer, fill it up with a lot of rendering instructions, and execute them. If you just need to do it once, you can do it in with graphics.execute command buffer. You always do that basically, but you can also attach yourself to the begin camera rendering from the render pipeline manager. That guarantees that this happens always before every frame. It has some disadvantages if you want to do fancy things. You don't have access to the standard matrices, and a lot of standard values are missing. So if you need them, you can manually feed them into your shader one way or another, but in the end, the output of the vertex shader, you put it in the SV position, in the regular shader semantics. You're in clip space, so -1 to 1, everything should work out as if rendered regularly. So, we are going to the grass and the trample. The grass, as I said, is the boring part. It's standard shell rendering. It is well, if you know shell rendering, it's basically just adding a lot of layers on top of each other and removing a little bit by the alpha so that it gives this kind of volume effect. Used since ages, pretty expensive, and now you can probably see why I remove as little from the terrain shader from the ground as possible, because we have a massive overdraw, a massive cost whenever something happens in the pixel shader. The start of this was actually a plugin that someone bought, but basically we rewrote it and rewrote it, so nothing of the original plugin remains, and this is why I call this the plugin of Theseus. There's some wind distortion. Yeah, it's both used on the real-time combat part and the strategy part, but the next effect is basically very much for the combat part. We have the trample, which is a modification of this grass. This is a purely visual effect, but it's my personal favorite effect. As you can see, it makes a huge difference just having the start of the battle, everything is cleaned up, and then at the end of the battle, you can basically see where armies were moving. There are basically lines wherever they were moving. You can actually identify some of our units by their ground pattern. Yeah, all of the units damage to the grass. It's also a pretty cheap effect. As I said, we use this kind of frustum space. In this case, not, because we're limiting this to the playable area, and we cannot change any camera position. Because we have an overdraw here. We are drawing, we are not clearing the texture, we are every frame just adding to it. And that also makes debugging in RenderDoc kind of a weird thing, because it's not always saving the accurate state there and creates some artifacts. But in the end, we apply it, we remove the grass where the mask is, we do some sharpening with the tiling texture where it's just modulating it. You can zoom in pretty far, and the texture is too low res to give a very high detail there. And we have some blending with the ground color, nothing fancy there. For performance reasons, or not only for performance reasons, but because it's just one of those occasions where instancing is a perfect use case. And how that works out, I'm going to the next slide. Because we have a huge system for those. Basically, we have a system that is just responsible for maintaining the grass damage, the trample. And we can just call basically a single draw from, for example, a VFX that just does apply once. We have a lot of VFX, for example, or catapults basically creates an explosion, and in the middle, when everything is hidden by the nice VFX, we make a draw call that just applies the damage, and afterwards you have a nice damage texture there. On the units, which are updating every frame, we have basically a small script on it that permanently that has the current position and the last position and collects all of the data that is required for rendering the whole thing. In the system, now they are registered, and every frame, when updating the trample texture, we just basically put it in a giant array and put it in a compute buffer and put it to the GPU. And now we are getting to a weird concept, rendering without meshes. Kind of a lie. Of course, there is a mesh, but it's not created in Unity. It's not imported. It's not even code created on the GPU side. It never touches the GPU. The mesh is actually kind of hard-coded into the shader here. We actually have 3 quads that I'm indexing into. And it's just a draw procedural, which means that inside of the shader, instead of your usual position, vertex color, etc., you get instead just the vertex ID and the instance ID. And this way, when you call it, I'm just saying how much instances I have and how much vertices I want to render this with. In the end, then this is the draw procedure call. In the vertex shader, I can use the instance to get, basically in the middle you see it, I use the instance ID to get the whole data for this, this specific unit that from the command buffer that I just put in the whole list of those units. And I can basically get all of the relevant information out. And then I apply it to this basically manually hard-coded into the shader mesh and get basically the regular output of a vertex shader out of it, and from the basically, yeah, just a standard vertex shader output, and pixel shader is no different than any other pixel shader. So for the buffers, if you use anything with draw procedural, or generally if you use a command buffer, not command buffer, a compute buffer, or a graphics buffer, what is really important is that you keep your data aligned, because if it doesn't, then there are going to be problems. It's important. The layouting is basically, you have to look up for data padding, because not, for example, if you have a byte and then the next, and then a vector, there might be empty data inside of the struct that you have to account for when you build your data structures. That's just one thing that is important here. But I'll not go in too much detail. I'll go to the next effect, on the actual last effect, which is light veins. Light veins is quite a complicated, quite a beautiful, but not as complicated effect. It's basically, as I said, we have a dark side, and we have a faction on that dark side that basically has the cities that are connected by this magic energy. And this magic energy, again, rendered in this frustum space, connects the location. This need to appear by gameplay when 2 cities are connected. I'm actually rendering out 2 of those textures. One is actually what you can see on the ground there. It's just part of the emissive texture. It removes grass where it is, so that it gets a nice out-of-the-ground look, like it's almost burning away the grass. And the second texture is for forest illumination, in case something goes on in the forest. There's additionally some pretty standard VFX stuff, like just a glow from the floor, which is a map, which is a mesh, just with a regular mesh renderer. There are some particles going on there. So for the path, we want to connect 2 locations. Now, if we just have a straight line, this probably looks very boring. So I'm basically taking the starting positions. I'm having a simple heuristic to bend the lines to avoid terrain. And that is by basically sampling the start and the end points, then calculating a middle point, how high it should be, and orthogonal to it, I sample 2 points. Those 2 points I'm using to basically push the line away into the when they are not on the even ground. Well, in the end, I get 3 points: a start, an end point, and a middle point. What can you do with this? Quadratic Bezier curve. This I'm getting away, getting again to the GPU. I'm transforming the meshes that I'm running with this There is some randomness involved in the texture. I mean, we have we have actually 8 textures. You can see 2 for this kind of rendering, and it just gets this kind of a real nice look for having a little bit of randomness in there and not everything is straight. And yeah, as I said, it's again in the mask, in the emissive mask, renders into the grass, removes grass wherever it is. For the shader, originally I did it completely just in code, but at some point, what happens when now someone else needs to work on it? What if it doesn't look right, or when someone else wants to do something like this? And this is where I basically took the existing shader and put it into Amplify. It needs to work in a system that is not supported by the standard templates from Amplify. So what I did is basically create a new custom template. If you look into it, if you know your way around shader code, it's actually quite easy to create one recommendation, look at it, create, if you have custom systems, create it so that your artists can also work with it. So, first illumination, as I said, the light veins, when they are under the forest, they are suddenly not visible anymore. So what do? We have this kind of lighting from below. This is, again, texture in this frustum space. We have a color, but we don't have an alpha actually here. What is in the alpha is not transparency, but is kind of a distance field again. And this way, we cannot have any shadows like this, but what we can have is we have the horizontal distance, we have the actual physical vertical distance, and this way we can calculate basically a distance drop-off, and we can also create this kind of cone shape mathematically, multiply them, and you get what you get on the light side, this nice cone coming out of the floor. Yeah, that is basically how this fake lighting is working here. Last thing is we are going to the kind of conventional VFX. When you connect 2 locations, of course, there's this light vein building up. There is a VFX, but a lot of this looks quite conventional, but there are some problems. Of course, if you ever built a standard particle system in the Shuriken particle system, you know that there are no really curvy spawners. The solution for this was easy. I just saved it as a mesh. We don't need triangles. The mesh is not rendered, but if you think about it, a mesh is without triangles is just a collection of points, and the standard particle spawner can just take a mesh and use all of those vertices as the basis for spawning particles. They are also ordered, so that with the ordered spawning, we can basically have this transition left to right. We can have them on the same mesh spawn randomly. This is how the basically idle VFX works. And yeah, that's it from this side. I guess I've gone into a lot of details, and now I'm waiting for questions.